Hi! Time to get a little more crazy than usual for me. I have an invisible infrared laser that I am pretty sure will break a current record on my laser rainbow. I will test how close its power and wavelength are to the eBay listing, and also explain why this higher power is extra impressive for an infrared laser. Here's a brain teaser for you. Which laser emits the most photons? A 500 milliwatts violet laser or an infrared of half the power, 250 milliwatts? Let's find out. When experimenting with a laser, wear safety glasses suitable for its wavelength and power output, especially when using invisible infrared lasers. And don't breathe any smoke. Let me warm up with a laser that eBay recalled for safety reasons. A first for me and a bit of a paradox, since this should be the weakest of the infrared lasers I have bought on eBay. How does this policy-violating laser perform? Its wavelength is around 976 nanometers. Great, close enough to the advertised 980 nanometers. Its power is advertised as 1 milliwatts and under 5 milliwatts. Naughty naughty. But to the knowing, there are indications in the listing of 30 milliwatts. Here's how strong it really is. "23 milliwatts. I thought it would be a little more, but then I realized something. While the 2 batteries I put in the laser are not heavily used, they are not factory fresh either. Second try, this time with brand new batteries. Okay, now it is 27 milliwatts, closer to 30. A good example of how important fresh batteries can be for max power. But all in all, I don't feel like 27 milliwatts at 976 nanometers stands out enough to qualify for the laser rainbow. Though for future experiments, it is just nice to have an infrared laser that is not a fire hazard. Next up is a laser I do expect to set a new record at 808 nanometers near infrared. The current record holder outputs a respectable 178 milliwatts. However, you might have seen I have a 370 milliwatts laser at around 808 nanometers. The hair removal laser. Lots of info about lasers in that video, such as the little but important detail to know about in this warning. But the laser beam from this one is highly divergent after a fixed focus spot, and it can only be on for like 3.5 seconds at a time. So again, I don't feel like the beauty blasting laser truly qualifies for the laser rainbow. My strongest 808 nanometers laser is actually much stronger. The pump diode in the Laser Glow Hercules is a 2500 milliwatts 808 nanometers laser diode made by Enlight. That one would stand out on the laser rainbow as the 3rd strongest. I just don't have access to its internal infrared beam. What I do have is this eBay laser. Focused to a small spot, it burns electrical tape so fast that the video looks sped up. But this is real time. Surely this will beat the current 178 milliwatts record and even the hair-frying laser. Going by the listing, this laser is somewhere between 1 and 1000 milliwatts. Time for a reality check. Its wavelength peaks at 803 nanometers. That's fine, within a reasonable spec of ±5 nanometers for a direct diode laser without temperature control. How powerful is it? Max 614 milliwatts. With a battery charged to 4.1 volts. I have mixed feelings about that. Second try for good measure. This time with the laser power meter set to a manual range of 2 watts to avoid the annoying max bug in it. Alright, 614 milliwatts it is. I was hoping for something closer to a full watt. Maybe they had to dial it down in power to avoid overheating in this cheap laser host. 5 nanometers under nominal for a direct diode laser can be an indication of a cold running underpowered diode. More on the subject in an earlier video of mine. With that said, over 600 milliwatts of laser light is always a lot. I would like to see the invisible beam from it. If I use my home-built beam dump to hide the bright laser spots and remove the infrared filter in my camera, we might see the beam in midair. Not really. Air does not scatter infrared well, as explained earlier. A trick for enhancing beam visibility on a low budget I have used since I was young is dust. Still underwhelming for 600 plus milliwatts. If only I had some smoke. Wait a minute. Yes, there it is. An invisible beam made visible. After a short important message, I will show how this laser is strong enough to ignite metal and how you can calculate the enormous number of photons any laser emits. A huge thank you to all my patrons. Thank you so much for helping out. It's really appreciated and important for a niche channel with monthly quality uploads like mine. For just $1 a month, you can help me out too and get full access to all my posts on patreon.com. Link in the description. Thank you. Burning black tape is a relatively easy task, but igniting metal is not. Yet, I believe this laser packs enough punch to ignite steel, in the form of steel wool. Here's a pound of it, but I will use less, inside, on my dinner table. First, a try with the beam focused to infinity. No, metal is hard to ignite, with light. Now, with the beam focused into a small, intense spot. Beautiful, like a small firework. I think I can go a bit bigger without burning down the table. Oh, not a full burn and picky on spot size. I wonder how it can be improved for a complete burn. Looking at the fire tetrahedron, missing fuel is not the issue. Some of it was still left. The chemical chain reaction is also available. The burn continued by itself long after I removed the initiating heat source, the activation energy of the laser spot. But heat could still be the issue. A compressed lump of steel wool with a lot of strands touching each other can act as a heatsink, sucking heat, energy, out of the reaction fast by the decent thermal conductivity of low-carbon steel. The oxidizer, oxygen in the air in this case, could also be the issue. There might not be enough air or convection near the steel if the wool is too compressed. Fluffed steel wool might be the solution. Wow, that was more energetic and a full burn. I need a bigger water bath. I find it fascinating that nothing but light starts this sparkling metal burn. Click like if you do too. Obviously, a lot of photons on a small spot is needed for this. How many photons does this laser actually emit? The formula for calculating it is fairly straightforward. The tricky bit is dividing by a very small number, Planck's constant, giving a very large result. However, the Windows calculator can handle this just fine in one go in its scientific mode. The number of photons emitted by the 614 mW 803 nanometers laser is... oh my! .5 quintillion photons per second. That's 2.5 millions photons a second. No wonder the light from this laser makes an impact. From the formulas, we can also tell that a longer wavelength equals lower energy. Infrared light carries less energy per photon than visible and ultraviolet light. Brings us back to the intro question: which one emits the most photons? The half-power infrared laser emits 21% more photons, making it the winner. Did you guess right? This explains why the infrared lasers are not the strongest in my collection. IR lasers have to emit more photons than the visible lasers just to match their power. Until we meet again in the next video, I recommend watching the video on the infrared hair blaster. Hope you enjoyed this video enough to click like and perhaps subscribe for more like it. In any case, thanks for watching. Bye for now.